3.5 Rational functions and their graphs. Find the domain of the following rational functions. All right, so domain, there's a limitation on the domain of these. Possible x values that will make the denominator equal to 0, and we can't have that. Okay, so I would set the denominator equal to 0 and find what possible x values would make the denominator equal to 0. So we just set the denominator equal to 0 and we solve. So plus 7, cancel, cancel, x is equal to 7. So we know that x cannot be equal to 7. So if we put it in, we can do like this, x such that x is not equal to 7, or we could do little interval notation, in which case we're going to have a hole, we're going to have a hole right at what x cannot be equal to. So in this case it would be a 7. Then union that with another 7, and notice that the hole right here is what x cannot be equal to, right? So again, x cannot be equal to 7, and you see that the little parentheses indicate that it approaches but is not equal to 7 on both sides. So we have negative infinity to 7 but not including 7, union 7 but not including 7 up to positive infinity. Okay, so that's the domain of the rational functions. So we do the same thing over here. We set the denominator equal to 0 and we solve it. So since this is a quadratic, meaning there's a 2 right there, so we're going to first set it equal to 0 to solve it, which we already did, and then we're going to factor it as the second step. Okay, so now we're to the factoring stage. This is the difference of squares, so we're going to say x minus 8 and x plus 8, right? So we set x minus 8 equal to 0, plus 8, plus 8. You can just flip the sign, that's fine. X is equal to positive 8. And then you say x plus 8 is equal to 0, minus 8, cancel, cancel. X is equal to negative 8. And we know that x cannot be equal to either of those. So a couple of ways to do this. We could say x such that x does not equal negative or positive or negative 8. So that'd be a compact way of doing it. Or we can do it in interval notation, so negative infinity up to, we have to hit the first one, which is negative 8, and then union, and then we have a hole at negative 8. But this is a little bit different in that we don't just have a hole at negative 8, right? So here's one hole where x cannot be equal to negative 8. We have another hole where x cannot be equal to positive 8 either. And it goes off to infinity. So this one actually has a couple of holes. So here we have our other hole, because the parentheses don't include it. So then over here we say, well, x is not equal to the a, right? I'm just putting these little things down here just to clarify. The actual answer would be either this or this. You don't actually put down x does not equal to negative 8 and x does not equal to 8 underneath it or anything like that. You just write down the interval notation with the union symbols. Okay, so let's try the next one. Now the next one, I could set the denominator equal to 0, but the thing about this one is you can't solve this. There's no real answer to this. There's nothing I can plug into that x squared plus 2 that is going to make it equal to 0. If I plug a 0 squared, the 0 plus 2 is still 2, which is not 0. If I plug in a negative, it's just going to flip it because I'm squaring it to a positive. If I put in a positive, it will maintain being positive. So there's nothing that will actually make this true. No real number will make that true. So this right here is just going to be negative infinity to infinity if we're doing interval notation, which is probably what you're going to do. So we'll just leave it at that. Now, once you find out what the denominator cannot be equal to, you need to determine whether or not, in this case, they're going to ask for vertical asymptotes, and they want to know about the holes. Okay, so if nothing cancels out, those are going to be vertical asymptotes once you find the limitations of the domain. If something does cancel out, that's going to be a hole. But either way, you have to find the limitations of the domain first. So we set the denominator equal to 0, we say x is equal to 0, and x plus 1 is equal to 0, minus 1, cancel, cancel, x is equal to negative 1. Okay, in this case, we have two holes in the denominator. Now, notice that nothing will cancel out with it x plus 3 in this case, right? So we literally just have vertical asymptotes. Whoops, I'll do a lowercase. You're going to have vertical asymptote at x is equal to 0 and negative 1, right? So those are the two ones. I guess I could separate it like this, right? So you have two different vertical asymptotes if you listed them out. Doesn't matter which way you order it, but in that case right there, right? Okay, now let's try the next one. Okay, in this case, I want to factor the numerator, and that would give me x plus 2 and x minus 2. We still have the denominator. You still need to set the denominator equal to 0. So let's do that first. I'm not going to get too far ahead. So my x minus 2 is equal to 0, plus 2, cancel, cancel. x is equal to positive 2. So what we know is that the denominator cannot be equal to that positive 2. Okay, so we did find a limitation on the domain. So the only question is, well, is that going to be a vertical asymptote, or is it going to be a hole in the graph? And in this case, since the x minus 2's actually do cancel out like this is going to be a hole. So there's going to be a hole at x is equal to 2. So whenever x is equal to 2, there is going to be a hole. Okay, so let's try the next one. Same kind of situation. You're going to have an x minus 7 in the numerator. Keep that. We factor the denominator, x plus 7 and x minus 7. Okay. We still need to set that equal to 0 and solve it. So x plus 7 equals 0 and x minus 7 equals 0. So minus 7, cancel, cancel. X is equal to negative 7. You can just flip the signs in this case. You don't have to write all this out. And then you have x positive 7. Okay. Now, here's the difference. The negative 7's cancel out, right? So in this case, the one that canceled out, in that case, that's going to be a hole. So there is going to be a hole at the one that canceled out. So the hole is at x is equal to 7. Now the other one, you're going to have a vertical asymptote. Asymptote at x is equal to negative 7. Okay, so we just differentiate. So again, whenever something cancels out, that turns it into a hole. Whenever it doesn't cancel out in the denominator, that is going to leave you an asymptote. Okay, so we're asked to find the horizontal asymptote, if any, of the graph of the rational function. So in this case, they're asking for horizontal asymptote. There's only 3 possibilities. Top bigger than the bottom, top and bottom are the same, or the bottom bigger than the top. That's it. Okay, so in this case, the bottom, right, there's a 2 is stronger than a 1. So this one's going to have a horizontal asymptote sorry about my handwriting, at y is equal to 0. Okay, because again, the denominator is bigger. You know, we're saying, if you remember correctly, in this case, this is the n is less than m, or you know, smaller on top, bigger on bottom. It's not technical. I realize that's not technical term, but that's the concept, right? Let's try the next one. We have a 2 on top, and we have a 2 on the bottom. So they're the same, right? So what we do in this case is we have a horizontal asymptote at y is equal to, and we're going to put 28 over a 7. Then we simplify that. 28 divided by 7 is a 4. So it's going to be at 4. Okay, and that's when they're the same, right? Same on top, same on the bottom. And again, we're talking about the exponents. You're always comparing the exponents of these. And the last one over here, we are comparing the exponents again, but now we have it's bigger on top, right? And it's smaller on the bottom. And as such, no horizontal asymptote. No horizontal asymptote. So the top just flies off to infinity. It's not held in check by anything. So no horizontal asymptote. Asymptote.